So, hello everyone, and welcome back to my channel. I hope you guys are doing absolutely fine. So, in this video, I'm going to go ahead in calculating the time complexity of the recursive Fibonacci series that I've shown in my previous video. So, if you haven't seen those videos, I'll highly recommend you to go and watch that video first before heading over to this one. I will post the link in the description below. So, whenever we have, let's say we have a particular set of recursive function, a function that calls itself for a longer time, then how do we calculate the time complexity of that function? So the time complexity of recursive function is nothing but it's the time complexity of a recursive function is the number of times a function is being called recursively. So it is nothing but equal to the number of times the function gets called. So we already took in the previous video, I've already taken the example where n was equal to 5. I'll also write down the equation once again where f of n is nothing but f of n minus 1 plus f of n minus 2. So if we have, say, what will be the first function that is going to be called? We have f of 5. So then after that, f of 4, and after that f of 4 will be called, but it will be split into f of 3, and then f of 4 further divided into f of 3 and f of 2. And this function again will be further recursively called into f of 2 and f of 1. And this f of 3 will again be called as will be further divided into till it gets f of 1 and f of 0. As I've already explained in the previous videos, I'll post those links in the description below. It'll go to f of 1, and since it does not know what f of 2 is, it will also call f of 1 and f of 0. So here also we are going to have the calls, that is f of 1 and f of 0. And in f of 2 we are going to have f of 1 and f of 0. So let us go hierarchically of how many times or how many functions are getting called. So each time as we go, we look back into the depth of the recursion. Here the total number of functions that are being called is twice. That is the number of times so here there's a number of times the function gets called when we go down. So at the first it is called once, and then again it is called twice, and as we go down it is called 4 times, and here it is called 6 times. Since f of 1, we know the value of f of 1, and then it is called twice. So the total number of times the function is getting called is 3 plus 4, 7, 13, and 15 times. So how do we calculate the time complexity? Usually the time complexity of a recursive Fibonacci is considered as O of 2 raised to n. Since you can have a look at the pattern, it is like first it is 2 raised to 0, and then it is 2 raised to 1, here it is 2 raised to 2, and here it is 2 raised to 3, and at the final stage it is has to be 2 raised to 4. And for the value n equals 5, it has to be 2 raised to 5. That means 32 times the function is getting called, which is absolutely wrong. So we cannot say that the time complexity that is usually mistaken to be O of 2 of n of recursive Fibo is not O of 2 of n. Then what is the time complexity? For understanding the time complexity, we need to have some background or some mathematical background based on what is a recurrence relation. So what is a recurrence relation? Fibonacci series is an example of an homogeneous recurrence relation. So what is a recurrence relation? We have f of n equal to f of n minus 1 plus f of n minus 2 has the equation for our Fibonacci series. So this is an example of homogeneous recurrence relation where n depends on its previous values, n minus 1 and n minus 2. So we can define a recurrence relation as a relation which depends on its past values. So coming over to one of the most basic homogeneous set of recurrence relation, we can write it as x of n equals a of x of n minus 1 plus b of x of n minus 2, where x of n is any set of function. So then we have two sets of roots. Let's say the roots of this equation is s of n comma t of n. So we can write s of n in the form of this above equation as a of s of n minus 1 plus b times s of n minus 2. And then we can also write t of n in the similar fashion, that is a of t of n minus 1 plus b of t of n minus 2. Then let's have two set of constants, that is c1 and c2. And let's try putting the above equation in, let's write the above equation for this value, that is c1 s of n and c2 t of n. We are now trying to find the solution of this recurrence relation, and this is one of way to prove the solution of a recurrence relation. This is like, we can write it as c1 s of n, c1 of the above equation. We're substituting the above equation, that is a of s n minus 1 plus b times s of n minus 2. And then we can write t of n, that is c2 times a of, substitute the value of t of n, that is a of t of n minus 1 plus b times t of n minus 2, b times t of n minus 2. That is the equation. So all we need to do is to bring the a values together and b values together. So we are just going to expand this equation and write it as c1 a of s of n minus 1 plus c1 b of s of n minus 2 plus, we can write this as c2 a of t of n minus 1 plus c2 b t of n minus, t of n minus 2. So let's bring the a terms together. We will have a c1 s of n minus 1 plus, we're surely going to have c2 t of n minus 1 plus, we'll have b of, we'll bring b terms together. So we have this term and this term. So we have b of c1 s of n minus 2 plus c2 t of n minus 2. So do you see that the equation that is above is similar to this equation, where x of n minus 1 is this term and x of n minus 2 is this term, which can be further written as where x of n will be, that is, the solution of this equation is c1 sn plus c2 tn. So that will equate to this equation, and that is the solution of recurrence relation. So in the next video, I'll complete the time complexity of recursive Fibonacci series. Thank you for watching. Please like, share and subscribe for more interesting content. Thank you and have a nice day.